AK Sengupta sir, am I audible?
Yes. Good evening, everyone. Yes, you are audible.
Okay. So the next session, session 4, we are starting now. Miss Khushbu Bharti, introduce sir.
Thank you, sir. A very good evening to one and all. Welcome to day two, fourth technical session of 6-day online faculty development program on electric vehicle and charging station technology for sustainable development sponsored by AICTE ATAL. Today's technical session is on power factor control for EV charger, and our resource person for this session is AK Shan Gupta, sir. On behalf of the organizing team, I welcome you, sir, in our today's technical session. Before you start your expert lecture, I would like to share a short biography of you to the participants. He had joined Crompton Greaves as an assistant project engineer in 1976 and handled various projects with Indian Telephone Industries, Nani, Allahabad Unit, IFFCO, Phulpur 400 kV switchyard, Sultanpur, etc. from 2003. Started own company in the name of Delta Power and Engineering Company, which has earned a value reputation in designing and manufacturing of power and distribution transformer, along with up to 7.5 MVA furnace transformer, also various capacity of power distribution board, MCC and APFC panels, etc. From 2020, the above company converted to the LLP farm in the name of style as Delta Shan Techno Ventures LLP. Now, Mr. Sengupta sir, holding the post of managing partner and CEO of the said company. With this, I would request you, our expert AK Sengupta sir, to kindly enlighten us with word of wisdom. Sir, please, you can continue.
And good evening, Kuzmu. Thank you very much for introducing me.
Start your
So, good evening, everyone. I'm just going to share the PPT, which I'm going to talk with you coming 1.5 hour. Next. Yes.
Okay.
Okay. So, but our topic is the theme of this total 5-day faculty development program that we have electrical vehicle and for charging stations and various things. So first of all, think we have to come for the slide 2. So the theme of this total FGP is electrical vehicle and charging station technology for sustainable development. Under that, we are trying to find out a particular load flow method and optimizations for power flow using the evolution techniques. So let us start with the slide number 3, where we have to tell you the sustainable development. It's a very important part for our electric vehicle systems. So what do you mean by that, sustainable development? So sustainable development is a concept that refers to meeting the needs of the present without the compromising the ability of future generations to meet their own needs. It emerged in response to growing the concerns about the environmental degradations, social inequality, and economic instability. Sustainable development seeks to balance the 3 key pillars. What are those 3 pillars? The first one we can say is a social inequality, economic instability, and sustainable development, which seeks to balance 3 key pillars. The first one, what I told, that environmental sustainability, social equity, and economic development. Now, what do you mean by environmental sustainability? So if you try to start the electric vehicle concept, we have to understand the fundamental things of sustainable development. So first point we can discuss about that sustainable development is environmental sustainability. Actually, this involves managing the natural resource in a way that preserves ecosystems and biodiversity, which can reduce pollutions and mitigates the climate changes. It emphasizes responsible consumption and production, renewable energy, conservations of water, and land restorations. In similar way, apart from environmental sustainability, even we can also have a very important point under that sustainable development, which is nothing but social equity. What do you mean by that social equity? So social sustainability focuses on ensuring that all people, regardless of background, have access to the basic needs like education, healthcare, and opportunities for economic participations. It also stresses the importance of reducing poverty, inequality, and ensuring social justice and inclusions. And the third and most important point is economic development for installing EV at various places, so that economic development is also a very important point. So sustainable development requires an economy that promotes growth, but does so in a way that does not deplete natural resource or harm the environment. It encourages innovations and the creation of green jobs and sustainable business practices while prioritizing long-term sustainable stability and over short-term profits. You will be knowing this coming 2030, the agenda, what they have written for like sustainable development goals, SDGs. So in 2015, the United Nations adopted the 2030 Agenda for Sustainable Development, which includes 17 sustainable development goals. These global goals aim to address the urgent challenges facing humanity, such as poverty, inequality, health, education, and climate change, and environmental degradations. The SDGs are universal, integrated, and invisible, meaning the actions toward one goal often support progress towards the others. Now, what do you mean that we are talking about the first point, that introduction of sustainable development? We're not going in depth, but we are just focusing on the basic idea for electric vehicles industry, how things are coming into the picture. What are the important changes? The climate change mitigations, resource conversions, and quality of life. Coming for the second bullet, we have seen the electric vehicles. So everyone almost know a few or more details about the electric vehicle. So what is electric vehicle? So an electric vehicle is a type of vehicle that is powered by an electric motor, which use energy stored in rechargeable batteries. Unlike conventional vehicles that rely on internal combustion engines fueled by gasoline or diesel, EVs run on only electricity, making them a cleaner and more sustainable transportation options. So this is the basic what you call knowledge for an electric vehicles. So in third bullet we have like what are the types. We know that there are various type of electric vehicles are also available, which is present on this what you call in daily day-to life. So first we can say as a battery electric vehicles, everyone knows, and short form we used to say is BEVs. So these vehicles run entirely on electricity stored in their batteries and have no internal combustion engine, and they must be plugged into an external source of electricity to recharge. Examples include the Tesla Model 3, Nissan Leaf, and Chevrolet Bolt. Second, apart from battery electric vehicles, so second types of electrical vehicles we can say is a plug-in hybrid electric vehicles. So in short form also we sometimes used to say PHEVs. So plug-in hybrid electric vehicles combine an electric motor with a gasoline engine, and this electric motor can power the vehicle from shorter distance, and when the battery runs out, the gasoline engine takes over. Example, we can say that it's include the Toyota Prius Prime and the Ford EcoSpace plug-in hybrid. And another type of electric vehicles is hybrid electric vehicles. So unlike plug-in hybrid electric vehicles, these hybrid electric vehicles don't need to be plugged into recharge. Instead, they use both electric motor and the gasoline engine, with the battery being charged through the regenerative braking and the engine itself. And the Toyota Prius is a well-known example of this type of electric vehicles, which is run by the in Gulf countries. And another type of electric vehicles is fuel cell electric vehicles. What is this fuel cell electric vehicles? These fuel cell electric vehicles use hydrogen fuel cells to generate electricity, which powers the motor, unlike battery electric vehicles, which rely on only battery, that plug-in hybrid vehicles that produce electricity through a chemical process that combines hydrogen and oxygen, emitting only water vapor. An example, this type of vehicles is Toyota Mirai and Hyundai Nexo. Next point is like overview of electric vehicles. That is the classifications we have discussed. Now, what are the key components of electric vehicles? So we know that there are various key components like electric motor, battery pack, inverter, and that inverter, then charging port and onboard charger, transmission like single speed gearbox, regenerative braking systems, power electronics control, and battery management systems, thermal management systems. So these are the key components of electric vehicles. So I'm not going in depth, but I'm just trying to give you a brief idea about that electric motor for key main components of electric vehicles. The electric motor is nothing but the heart of an electric vehicle, as we know, responsible for converting electrical energy from the battery into the mechanical energy to drive the wheels. And normally these electric vehicles typically use either AC, alternating current, to DC motors. AC motors more common in modern electric vehicles due to their efficiency and ability to handle higher speeds and power demands. The first component, what we discuss about electric motor. So as we understand, so this is the heart of an electric vehicles. So what are the other components? Battery pack. As we know, the battery pack stores electrical energy used by the electric motor by propel the vehicle. And the most common type of battery used in electric vehicle is the lithium-ion battery, which offers a good balance of energy density, weight, and rechargeability. And this battery is one of the most expensive components of electric vehicles, but advances in battery technology are helping to reduce the cost and improve energy density, resulting the longer driving ranges. I think everyone, we have some of already have using the electric vehicles. So whatever the car purchase, the cost, the battery, almost the 60% of the cost is coming to the battery pack. Third important component of electric vehicles is inverter. So our speakers already told in depth, but I'm just giving a brief idea. Inverter. So what inverter is in electric vehicles? The inverter is an essential component that converts the DC electricity, which is stored in the battery, which is converted to AC electricity power to the motor. Now, can you please come to the next slide? Okay. So now, as we are using what you call electric vehicles, so we should understand that what are the advantages we have for electrical vehicles. So you know the advantage of electrical vehicles. It is a very natural thing, and from here we got so many advantages. So what are the advantages? So advantage is first, you can say the reduction of greenhouse gas emissions, energy transitions, grid flexibility. So these are the very important thing. And economic impact, you know, this economic impact, and like if you go that what you call, okay, let us just start with that environmental benefits. So what the environmental benefits? Environmental benefits, like we have no direct carbon monoxide CO2 emissions, and which can also reduce the air pollutions, and also it is try to what you call minimize the noise pollutions. because we have seen diesel engine car, petrol engine car, and as also will compare to the electric vehicles, you can feel the sound difference. So whenever a car is passing electric vehicles, you never understand that a car is passed just beside you, because with very less noise and the lower overall carbon footprint, which charged with the renewable energy. And energy efficiency, that is also a very important factor for these electric vehicles. So EV are more energy efficient than the conventional vehicles, and EVs convert over 85 to 90% of the electrical energy from the grid power to the wheels, and compared only 20 to 30% of the gasoline engines. And what is economic impact? So economic impact, you know that after some time, we are not able to use those non-conventional energy sources. So it's a lower operating cost, so fuel and maintenance. So normally we have seen when you go for the what you call petrol and diesel engine, so every year, alternate year, we have to maintain those vehicles. But if we use those electric vehicles, so these operating and maintenance cost is very low, and long-term saving consumers and reduce dependency on fossil fuels. Please come to the next slide. Now, this is also a very important thing, charging stations technology. So what is charging station technology? So charging station technology is nothing but types of charging stations. So there are various forms. It was shown in the slide, level 1, level 2, and this is fast charging we have seen. Suppose level 1. What is level 1? It's a slow charging. What is that? What is the rating and other things? There is a standard household outlet like 120 volt, typically used for the overnight charging. Suppose we will just run for any particular purpose 70 to 80 kilometer now. Night I won't run my vehicles. So what I did, I just go for the slow charging, and it is also available from the household. Just plug and play, plug and go for the overnight charging. So that is nothing but level 1 charging. What is level 2? Fast charging. So it requires a dedicated 240 volt outlet that are more common in homes, public locations, and workplace, and charges in EV faster than level 1. So we can see that level 2 charging time is faster than the level 1, and it is a dedicated 240 volt outlet. But in level 1, it was only household standard 120 volt DC fast charging. So we know if you go to any particular charging stations, petrol pump or other dedicated portions, if you go for 45 to 50 minutes, almost 90% my electric vehicles is what you call a charge. So this is very high speed charging up to 350 kilowatt, okay, and used for long trips, found in highway stations, and it can charge up to 80% within 20 to 30 minutes. So these are the types what we have discussed for charging station technology. So key charging technology, what is that? So it was like connector standards. What is connector standards? So it is nothing but the plug type, that is type 1, type 2, CCS, CHA demo, and Tesla supercharger. So this is the connector standards what we commonly use. Smart charging. What is smart charging? It allows the schedule of charging times, monitor the battery levels, and optimize charging the costs. And obviously wireless charging. So it is an emerging technology that charges electric vehicles via electromagnetic inductions. Okay. Now come to the next what you call that bullet. Sorry, just go back once again. Sorry. The role of charging station in EV adoption. So that is very important thing, that what role we should play for charging station for adapting in EV adoptions. So the expanding and optimizing the ability of the charging station is crucial to accelerate the EV adoptions and integration of charging station into urban planning, homes, and workplaces. And that what you call what is the important role for charging station for adoption? It is a reduction of greenhouse emissions. So EV is powered by renewable energy source, solar or wind, that can help reduce the transportation sector's carbon emissions. And EVs also contribute to cleaner air, particularly in urban areas with high vehicle density. And energy transitions, this is also an important role for installing a charging station, EV station. The EV are part of the broader of the transition of clean energy, and the importance of integrating renewable energy generation and energy storage systems with EV charging network. And grid flexibility and vehicle to grid. So V2G technology allows electric vehicles to return the electricity to the grid during the peak demand periods, contributing to the grid stability. And smart grids are also demand response mechanisms will help balance electric vehicle charging with renewable energy in a productions. Please come to the next slide. Okay, this sorry, this already I have told that reduction of greenhouse emissions, energy transitions, grid flexibility. Just now we discussed. So smart grids are demand response mechanisms what help the electric vehicle charging with the renewable energy productions. Come to the next slide, please. The future of electric vehicles and charging station technology, the next generation batteries, autonomous EV, these are the smart cities. Okay, so let us start with the next generation batteries. So what will be the next generation batteries? So it will be solid state batteries, fast charging batteries, and higher energy density batteries to improve range and reduce the charging times. So that is the future, but we are thinking for next generation batteries. Autonomous electric vehicles. What is that? Autonomous electric vehicles. Actually, it is nothing. The integration of the self-driving technology with electric vehicles could enhance efficiency and reduce congestions. So that is nothing but autonomous electric vehicles. And the third one, in integration with smart cities. So charging stations and EVs are part of the larger smart city ecosystems. Opportunities for sustainable urban mobility, such as shared electric vehicle fleets. Please come to the next slide. Okay, so here actually after this slide, just we are trying to say like how whenever a charging station is going to be installed in a particular area, how we try to locate, and randomly we cannot install what you call charging stations here and there. So there is some basic what you call rules and other parameters should be there. Otherwise, the power systems it might affect. So on the next slide, it was just shown a distribution system. So where we have trying to show actually what will happen to the load flow, and if a load flow for a power systems, when a power is coming from the grid, then is coming to the consumer grids, how is power is going to flow from the generation and to the customer ends. Please come to the next slide. Come to the next, please. Please, next one. This is not required. You can see. So these are the like what you call that most integration of the distributed resource, like hydro, wind, solar, geothermal, biomass, ocean energy, fuel cell. So this also it's a terms of non-conventional energy sources what we can use for our systems. Please come to the next slides. And the diesel generator set, which is mainly considered as the active power source, which compromising investing the distribution system to meet up the active power demand and to the maximum profit. And we are trying to see the active power, which can result in efficiency of fulfilling KVR and reactive power load requirement. And normal thing is that whenever the voltage collapse happen, and if we try to randomly like installed shunt capacitor or DG into the system, so there is a unique technique is available to install those devices into the systems. So we'll try to see for the coming slides like how we are trying to give the locations through optimization techniques. This is evaluation optimization techniques, though these techniques will be shown in the upcoming slides. Please come to the next one. So these are the literature review. Please come down. Okay, so actually for distribution systems, when you are trying to go for the distribution system, so we are trying to put this point when you are trying to build, so we have to check that it should have the maximum distribution system efficiency and reactive power management to the deregulated power market and reactive power management in present of the distribution generations. Next, come to the next slide. Actually, for this particular slide, they have shown like whenever a power is flowing from the substation to the grid, if the power is coming from the grid to the customer end, the power sometimes it is a drop because of that what you call the losses. And to reduce the losses or to what you call to improve the loss, what we have to do, we have to install the DG and shunt capacitor. And DG it may be in case of what you call that non-conventional energy source, like we can use the solar power, we can use wind power, and sometimes we use active power source, sometimes we use reactive power source. So integration of both active and reactive power source, nothing but DG and shunt capacitor into the systems, and we try to see before installing those DG and shunt capacitor into the systems, and after installing, we'll try to verify if there is any voltage dip, how we'll try to manage or try to improve those voltage profile or to minimize the loss. Please come to the next one. Motivation is just same thing. Please come to the next one. Okay, so actually this is the main objective, is to develop the new algorithm for power flow analysis with faster convergence characteristics than the popular algorithm available in the literature without sacrificing accuracy of the situation. So our main intention is the location, to find out the exact locations, and at the same time we try to find out the algorithm technique, and which will converge very fast and the lesser time, and without varying any accuracy. That means accuracy should be in as it is, but at the same time we will develop an algorithm so that it can run fast, and it will give the almost 100% accuracy. Please come to this one, next one. Okay, so in this particular thing, you have seen these are the algorithm. We have just one differential evolutionary algorithm, binary particle swarm optimizations, binary gravitational search algorithm, and binary version of collective animal behavior algorithm. So everyone know differential evolution algorithm, particle swarm optimizations, gravitational search algorithm, and what you call collective animal behavior algorithm. Actually, so these algorithms it was there in the literature or some research. What we have done in this particular work, we have just identified the location. So for identifying the location, so somewhere we have to give yes, or somewhere we have to give no. So in that way, for algorithm, we are trying to convert in binary format. Either if it is exist, it will be 1. If it is not exist, it is 0. So that's what the term came binary. For every optimization, it comes binary version. So it will be either 0, non-existence, 1 is existence. Please come to the next slide. So these are the typical systems and what we have worked. So this is the IEEE 10 bus, 12 bus, 28 bus, 30 bus, and 33 bus, 69, and Indian 25 bus systems we have worked on, and we have tried to integrate those or what you call active power and reactive power, and we try to find the best positions. If we try to fit that best position, so we can able to understand where the power is flowing very accurately. That means loss is minimum and voltage profile sounds good. Come to the next slide, please. This is another type of systems. One system, previous slide, it was a balanced systems, and this systems, this particular slide, it shows the unbalanced systems, because normally in our theoretical and practical there is something different. In our theoretical, we are always try to go for the balanced systems, because for calculation and other purposes. But when you come to the real world, then you can identify the actual things. So actual thing is unbalanced one. So all phases are unbalanced for these unbalanced systems. So those are the particular systems which is found, and we have also worked in this for unbalanced systems. Please come to the next one. Okay, so it is the chapter 1 where we have shown a load flow analysis for radial distribution systems. It has shown for the balance and unbalance. Please, it's not needed. Okay, why we have come for the next slide. We come to the these diagrams once again, please. Slide number 25. Okay, so let's check this. This is a particular systems. You can see that V0 is a grid bus. Okay, from V0 to V1 to V2 to VK up to Vn. So the bus, the initial bus is V0, where we have take this voltage as a grid voltage 1 per unit, and after that second bus means V1. So that bus voltage is nothing but the bus voltage from 1 and minus the what you call the losses from 1 to 2, that will come to the V1. Then once we'll get V1, then loss, resistance loss, reactance loss will come to Vk. Up to this one will go to the V0. But you can see from V1, one more particular load is there, PL, PL. So it is nothing but active power load and reactive power load. So every bus might have some loads, and you have seen that there is a capacitor symbol. So it was shunt capacitor. It was added to the particular bus number 2, means V1. And here also you can see bus number VK. There was a one more bus is going to the VK1, V2. So this from V0 to Vn, like V0, V1, and dot VK dot VK. So this straight line, it is called a feeder, and from VK to what you call VK1 to VK1, that is called a lateral. Okay, if anything is coming from VK1 to downwards, so it will be sublateral. So it is a single line diagram for a distribution systems, where we have shown a grid bus from where the power is coming and to the consumer ends. Consumer ends means V0, where we are standing, we are taking that power. So the power or the power is coming from that long such level, and that voltage what we are getting from like a V0, we are not able to get that Vk. So there is a significant loss. Loss means very minimum, but that loss should not be there. Because of what? Because of it is nothing but what for resistance and reactance. So that's what we have tried to identify, how to minimize those losses, and how to improve if there is any loss, how to improve. So if we try to integrate those what you call non-conventional energy source, either diesel generator set, or you can say install a small solar power plant, or wherever wind is there, we can try to install a wind power stations and try to boost up those what you call that voltage to the system, so that voltage level should maintain a what you call almost near to whatever the bus voltage you are getting for the grid bus. Okay, so let's come to the next slide. So these are the basic equations or assumptions what we have seen for P and Qn. P and Qn is nothing but that last 10 bus, where we have assumed that at the main feeder, the lateral subreference, and the voltage is VKU, and the formula is given, and the real power loss, how you try to find out the real power loss. So in the coming slide, please come to the next slide. Here also you can see the reactive power loss, and those are the initial conditions for getting the power flow. We have assumed P0, how to find out P0, how to find out Q0. So these are the formulas given 2.5 and 2.6. Come to the next slide. Okay, so after that, P factor and Q factor. P factor, Q factor, nothing but real power factor, Q power factor. After getting P factor, Q factor, we'll try to evaluate the bus voltage magnitude. That was important. Come to the next slide, please. Okay, so P0, Q0, initial value conditions. Come to the next one. Okay, so this is the equations for real power flow. This is the equation 2.12 and equation 2.13. That one are also so the reactive power flow. It's a very simple thing. I and I plus 1 is nothing but the consecutive two bus voltages, what it was showing. Come to the next slide, please. Yes, so the ultimate aim is to computation of the bus voltage, which was given is equation 2.14. After getting P0, P1, then Pi plus 1. After getting, then we are trying to find out what are the bus voltage is for the consecutive buses. Come to the slide, next one. Okay, so we'll just discuss particular any one systems. So these are the systems, not record all the systems. let us come to the one particular system. Come to the please 33 number slide. Okay, so you can see it is a comparative load flow solutions what we have done through this algorithm. So bus number 1, you can see the grid bus voltage. So every one it was shown is a 111, so 1 per unit. So our proposed method also it has shown the literature which is available in the 17 and 21, that is also given. You can see the last bus voltage. Last bus voltage means bus number 33, last one. You can see we have gone 0.9180. So that is significant, slightly improving. That means we are trying to reach the last bus voltage very near to the grid bus voltage. So so this is the tabular column. If you can't find the thing, the picture will say you something about the how we'll try to develop the new load flow algorithm which is giving the more accurate. Please come to the slide number 34. See, so you can see so node voltage this method and node voltage by the proposed method is almost same, but slightly you can see from bus number 4 to bus number 17 there is a slightly upwards the bus voltages. Okay, so come to the next one. So this is another test systems. So these particular test systems where we have seen the bus number 1 to bus number 27, it is called a grid bus, and from bus number 2 you can see another bus is coming from 28, 29, 30, 31, 32, 33, 35. So these are called lateral. Okay, and you can also see from bus number 6 to bus number 52, 6, 51, 52, this is called lateral, and these all are the lateral buses. It is a typical system, 69 bus systems. In their 69 bus system also we have tried to find out the bus voltage, and we have compared so many things. Just come to the next slide. I'm not going in with the next slide. Just see the graphs. See, after comparison, this we have got like this comparative result analysis. Yes, now you please scroll what you call slides, few slides. This is unbalanced system, not required for this individual component models. So these are the modeling we have done for load. We have go for the modeling portions, line, voltage regulator, switch, transformer, co-generator, and shunt capacitor. We have modeled individually, and we have go for the load flow analysis. Please come next. No, just you please scroll down slowly. I'll tell you where you will please stop. Okay, so this is not required. This is in tape. This is not at all required for the time being. Come after 70 slides, 70. No, yes. So particle swarm optimization, you know. So this I'm just not going to say local based, global based. Change, please change. This is the position update. Okay, so I'll just give you this one. So what we did now, just now I told, so particle swarm optimization, differential evolutions algorithm, then gravitational search algorithm, then collective animal behavior algorithm. But the beauty of this research topic here, that every algorithm we made it in binary bit, and which is nothing but a 0 and 1 concept. So we can see that the term, the and/or operations, with this technique, that individual value we have made it in 0, 1 individual. So we have converted BPSU. So wherever you need to install a charging stations, it is needed. We cannot randomly fix a charging station. We cannot fit integrate a DG and shunt capacitor into the system. So there is a basic laws in behind where we have to place accurately so that we can get that good result. So these the particular systems which give you any optimizations will transform into the binary versions. Yes, please just scroll it. So these are the equations. These are the equations. Once again, the same thing is repeat for the different terminology. So okay, so this we're trying to see in a graph where we have seen that normally when we have go for the TLL means total line loss. So when we are performing the test, so for normal power flow we have got only 403.0584 kilowatt. But when we use that binary version of particle swarm optimizations and we integrate the two, we have given 3 DG, or the location is also find out 2451 and the location, sorry, 253, and the shunt capacitor we have given in 400 each of 100. So we placed that location, and that location now what it is showing in table 4.2, it is not came randomly, it is came through that optimization technique. Which optimization technique? We have done through the binary particle sum optimization technique, and we have seen the total line loss is improved from 403 to 385, and whereas total voltage deviation is also improved from 1.7654 pu to 1.5467 pu, and the percentage improvement over NPF also we get 0.22 percentage. Okay, so in this way, in every aspect, every test session we have performed, and we have shown that for any optimization techniques and other particular portions, we are trying to improve the total voltage deviations and total things. Come to the next. Let me see the very similar things. So this particular graph come to the 79 ones. Okay, I'll just tell you the 4.5. So this is nothing but a convergence characteristics for a optimization techniques. Whenever we are trying to go for any optimization technique, we have to go for after a certain time for a 30 iterations, 70 iterations, or 100 iterations, 1000 iterations. At a certain time, we'll get that global based positions. So after that, whenever you increase or decrease, the value will not change. So that figure 4.5, it shows the convergence characteristics. It holds also good. Please come to the next one. Okay, so come to the next. So this is the very similar type of result for or location and what you call location they have also shown, and that rating also they have seen through this different optimization techniques. Okay, so okay, very similar to. So let it stop it here. Let it stop it here. I'll just put in summary here. So actually, normally the electric vehicles and charging stations are very crucial components in the move towards a more sustainable transportation systems. And to develop the charging infrastructure, no, we have to integrate the renewable energy and technological advancement in batteries are key to realize the full potential of electrical vehicles. And what are the actions we have to take? We have to actions. Actually, it will be giving the government, the businessmen, individual, which must collaborate to the expand of EV adoptions and build a comprehensive charging infrastructure. The future of the transportation and electric, and it is imperative to the support to the transitions for a cleaner, more sustainable one. And big challenges is that for the cost of the battery is more. So in that way also we have to think in a better way how to minimize this electric vehicle cost. And suppose everyone knows about the Ola and Uber. Right now, this 20%, 30% stake is also in the electric vehicles. Even that electric scooter is coming, e-rickshaw is coming. So in that way, if we try to, government is taking the proper actions for using more and more. So automatically, when demand will be more, then production has to be more. And we, if the researchers will try to find out or the what you call more battery charging stations and more strong battery backup, then easily and that for another coming 10 years, so we have a great future for electric vehicles. So for the time being, let me stop it here. Actually, from beginning to here, I'm just trying to overlook those two things, the electric vehicles and the basic things. I'm not going in depth, but I'm shown like where the charging stations and other particular things when we cannot put randomly here and there. But if you try to put randomly here and there, what will affect the power systems? So in that combined effect, I'm trying to give you a brief lecture about this particular topic. So if anyone have any questions related to this topic, so I'll happy to please give answers.
Thank you, sir, for your lecture. Dear participants, if you have any question or queries, you can unmute yourself and ask the question, or you can write in chat box.
Okay, thank you very much. I think I'm sorry for what the initial, I don't know what was the problem.
Sir, there is a question written in chat box from Mr. Vivek Kumar Singh. Sir, my question is related to power factor. How will it get affected?
See, it depend upon the load. See, when we'll try to keep those loads very changed to like resistive. That inductive load we have to reduce in such a way so that we can get the power factor very close to unity.
Sir, I request to enlighten us in the field of charging stations. So, like if we are installing too many charging stations in a densely overloaded distribution transformer, then how will the power factor get affected?
Because this if we randomly install that what you call charging stations, so normally the power which is dedicatedly coming from the substation to the consumer needs, it has a certain what you call that laws and other things. So as per the demand, we are trying to what you call individually we try to distribute, but without planning, if we try to install, so that will impact on the other parameters also. When the industry is running, the hospitals or school college, so that may get affected whenever we'll try to draw the more power from the charging station and without any proper what you call methodology.
Thank you, sir.
Thank you.
Another question
Good
is
evening,
there
sir.
in chat box from Mr. Yogesh. Can one some plan for DC charging station? Can someone plan for DC charging station?
Yes, you can plan, because right now the Tata Motors and other things, when suppose like suppose you have an apartment having 40 apartments and you have 10 electric vehicles with you. So if you call them we have 10 electric vehicles, very small price or other things, so they will install a charging DC charging fast charging station. They will try to install. Even in Kolkata also, there is some apartment we have seen, and they have also called that particular who is installing these charging stations. So they have shown like it's rapidly growing, but on the same time that they have taken the power, taken the permissions from the competent authority to approve to install those charging stations.
Good evening, sir.
Good evening. Good evening.
Sir, have you applied this novel binary optimization method to factor, sir?
Can you repeat once, Balaji? Novel binary optimization technique, where?
You have explained about the optimization technique, no, sir? The
Yes,
novel
yes.
optimization. Have you applied this to reduce, like to improve the power factor?
No, I have not gone to the improve the power factor, but I have tried to find out the locations. I have, with that optimization, I have tried to locate that exact locations where I can fix those integrated DG and shunt capacitor into the system, so that power, whatever the loss is coming, that loss has to be reduced a significant bit, and the voltage profile, it has improved somehow level, not gone to the power factor.
Okay, sir. Thank you.
Okay, Devabrata, then I think thank you so much.
There is no sir. There is a question
Oh,
in chat
okay.
box also.
Okay, disposing batteries also determined and how we can say. Yes, that is true thing. That is true thing because if you try to think that everyone we use for like for the electric vehicles and every 5 car out of 10 car, so disposing is a big challenge that no one can what you call deny. And but compared to the other things, still it is in upper hand, I can say.
Any other question from participants? You can unmute yourself or you can write in chat box. Okay, sir. Thank you, sir. I think there is no question from audience or participants. So thank you for being with us. Thank you all of you, the participants. Sir, there is.
Thank you. Devabrata.
Okay, thank you to all of you and good night to all of you. Yes, sir.
Thank you. Good night.
Done today's topic. So in day 3 we have to start our next session 5 from 6 p.m. So be with us. Thank you to all of you and good night to all of you.